Welcome to today's deep dive. We really have a fascinating mission today for you.
Yeah, it is quite a ride.
It really is. We're going to unpack a highly detailed, meticulously argued, and frankly, a pretty unorthodox translated blog post.
Right, from an author known online as Zionade 2023.
Exactly. And the core premise of this deep dive is a massive what if. Like, what if theoretical physics, and we mean including the foundational work of Albert Einstein, has been fundamentally flawed for over a century?
It's a small claim.
Right, no big deal. But the author argues it's flawed simply because physicists have been, well, slacking, basically ignoring the physical reality of how a camera actually gathers information.
Yeah, they argue that physics has been stuck in what you might call God mode.
God mode. Okay, so think about when you're playing a modern video game, right? There's usually a moment or a setting where you can detach the camera from your actual character.
Right, you enter that God mode, you just float up.
You float up, you look down at the whole digital world, you can see the enemies hiding behind the walls, and you just take in the entire map at once in this perfect, instantaneous freeze frame.
And I mean, the appeal of that perspective is totally obvious. You're completely removed from the physical constraints of the simulation.
Because you aren't a player bound by the rules anymore.
Exactly. You become this omniscient observer who just knows the exact location of everything simultaneously.
It feels incredibly powerful.
Yeah.
But eventually, you have to snap back into your character's body, into that first-person view.
Back to reality.
Yeah, and suddenly you can only see what is directly in front of your digital eyes. You have blind spots. If something happens on the other side of the map, you literally have to wait for the visual information, the light, to travel to your location.
You are bound by the physical mechanics of that world.
And that right there is exactly where the author claims theoretical physics went wrong. They stayed floating in God mode.
Which brings us to the sandbox illusion. The author actually traces this math obsession all the way back to Isaac Newton.
Okay, let's unpack this. What did Newton do?
Well, Newton defined what we call the inertial frame. The idea of a system moving at a constant speed as a sort of miniature garden.
A miniature garden.
Yeah, or like a sandbox world that's completely sealed off from external influences. And the critical flaw the author points out here is the reliance on instantaneous action at a distance.
Right, taking a page from the ancient Greeks, doing geometry.
Exactly. Building mathematical models where the distance between two moving objects could be calculated instantly. In his sandbox, gathering information just happens by magic.
The equation just sort of knows where everything is.
Right. It completely ignores the mechanism of light taking actual physical time to travel from object A to object B.
So then an observer can actually perceive it. It's like they're playing the role of a magician looking into a crystal ball, rather than placing a physical camera inside the world.
Yeah, they're hovering outside the simulation, drawing these neat geometric lines between planets or moving trains on a chalkboard.
Instead of putting a physical camera in that Cartesian coordinate system and waiting for the photons to actually hit the lens.
And the author points out that this is a symptom of just being way too math-obsessed. And to illustrate the danger of this mindset, they bring in Ferdinand de Saussure's structural linguistics.
I have to admit, when I saw linguistics pop up in a physics post, I was scratching my head. Like, how does language connect to the speed of light?
I know it seems like a leap, but it's brilliant.
Oh.
Saussure developed the concept of the signifier and the signified.
Okay, remind us how that works.
So the signifier is the symbol, like the visible written word dog, D-O-G.
Right.
But the signified is the actual meaning, the physical furry animal that barks and sheds on your couch.
Okay, I'm with you.
The author argues that theoretical physics has systematically conflated the two. Physicists have taken the mathematical map, the signifier, and treated it as if it were the physical territory.
Ah, they mistook the menu for the meal.
Exactly. Because their coordinate systems work flawlessly on paper, with lines connecting points instantly, they just assume the physical universe operates the exact same way.
They assume reality functions without a physical observer needing to wait for the light to hit their retina. And Minkowski gets called out specifically for this, right?
Hermann Minkowski, yes.
Yeah.
He was the mathematician who helped develop the four-dimensional space-time continuum that Einstein used for relativity.
Right, the famous space-time concept.
Well, Minkowski mathematically defined a concept called the past light cone. It's a geometric model of all the light rays from past events that could potentially reach an observer.
But the catch is he built this purely by definition.
Just drew the lines on the map. The author argues he lacked the physical rigor to place a real physical camera eye into that moving environment to track how the light physically travels through the void.
So if this God mode trap is so easy to fall into, How did the very first scientists who actually tried to measure light avoid it? Because that historical context is really crucial here.
It is. The text contrasts two historical giants here, Ole Romer in the 17th century and James Bradley in the 18th century.
Let's look at Romer first. The author seems to be a big fan.
Oh, absolutely. The author affectionately calls him Rumor Senpai.
Romer Senpai, I love that.
He's held up as the gold standard for his extreme caution. Rumor realized early on that you cannot separate the observer from the universe.
Right, he created a global coordinate system.
Yes, setting the sun at a velocity of 0 within the electromagnetic field, and he calculated the speed of light by observing the eclipses of Jupiter's moons.
Which is still wild to think about them doing that back then.
Truly. He noticed that when the Earth was moving toward Jupiter in its orbit, the eclipses seemed to happen a bit earlier. When Earth was moving away, they happened later.
So he deduced the mechanism perfectly. Light has a physical travel time, and the Earth, our camera, is moving through space while that light is in transit.
Boomer put the camera in the game. He didn't hover outside of it.
But then we get to James Bradley. Now, Bradley tried to measure the speed of light using a slanted telescope inside a building, right?
Right. And he calculated that the Earth's speed through the electromagnetic field was 1/10,000th the speed of light.
But the author claims Bradley made a massive conceptual error here.
A huge one. Let's dig into the how of that experiment. Bradley was measuring a phenomenon called the aberration of light.
Okay.
Since starlight is coming down toward Earth and the Earth is moving sideways through space, Bradley had to physically slant his telescope to catch the light straight down the tube.
Oh, this makes total sense. It's like walking in the rain, right?
Exactly.
If you're standing perfectly still, the rain falls straight down on your head, so you hold your umbrella straight up. But if you start sprinting forward, you run into the falling raindrops.
So to keep dry, you have to tilt your umbrella forward.
Right, and the angle of that tilt tells you the ratio of how fast the rain is falling compared to how fast you're running.
That is the exact mechanism of Bradley's slanted telescope.
Mhm.
The starlight is the rain, and the Earth's orbit is the sprint.
Got it.
So Bradley tilted his telescope, which the author assigns a physical length of 10 units to catch the photons.
The length of 10 is vital, right? Because it represents a physical distance the light must traverse inside the tube.
Yes, but here is the critical misstep. Bradley calculated the angle geometrically, treating his building as a local coordinate system perfectly at rest.
Oh, I see.
He treated the telescope as a stationary platform, ignoring the reality that the building, the telescope, and his own biological eye were all actively moving through the universe's electromagnetic field while the light was traveling down that length of 10.
He essentially forgot he was on a moving train. He localized his math and just completely detached himself from the global movement of the universe.
Exactly. And to prove why zooming out and looking at the physical delay of light is so critical, the author sets up this great thought experiment using 3 cameras.
Right, named after historical Chinese figures. We have Cam 1, Han Xin, located right at the event. We have Cam 3, Liu Bang the King, floating way above the action.
But the star of the show is Cam 2 Xiao He, the tactician.
Okay, so what is Zhao He doing?
Cam 2 is positioned at a physical offset from the telescope. The tactician's job is to observe the light, leaving the 2 ends of Bradley's length 10 telescope, and determine exactly where the telescope was at time 0.
But because Cam 2 is located at an angle and a distance away, the light from the front of the telescope physically reaches the camera lens before the light from the back of the telescope does.
Right. Xiao He receives a staggered set of visual signals.
And because he's getting these delayed, staggered photons, he can't just use a mathematical protractor and trust the instantaneous image he sees.
He has to reverse engineer the event. He has to trace those photons backward through space and time, calculating their transit delay based on his specific physical distance from the telescope.
To reconstruct its true position at time 0.
Exactly. It proves that local observation is inherently delayed and disjointed. You need a distant, physically positioned camera to prove the global reality of an object through the mechanism of light delay.
You cannot rely on instantaneous mathematical definitions.
No, because abstract math equations are brilliant at hiding these physical delays. The numbers on the chalkboard they don't care how long a photon takes to travel.
Which is exactly why the author actually abandons paper and pencil to prove this point right. They build a literal simulation using 3D rendering software.
Yeah, the author uses Blender, which is a highly complex 3D modeling program, to force the physics back into the physical realm.
The environment they describe is so vivid. It's this spherical cap with a semi-spherical dome ceiling.
And inside this digital space, the telescope isn't just a geometric line. It's a cylinder constructed of cyan-colored spheres representing individual atoms.
And these atoms are arranged in this zigzag pattern bouncing between the floor and the ceiling. But the most crucial detail isn't the telescope itself, it's the green lines stretching out from those cyan atoms.
Right, the author isn't just drawing lines of sight. Those green lines represent the actual trajectories of light rays physically traveling across the 3D space to hit Cam2.
And then the author does something really interesting. They manipulate the horizontal field of view on the camera, switching between 45 degrees, 90 degrees, and 150 degrees.
Which is fascinating.
Why does the physical lens of the camera alter the mathematical proof?
It alters the proof because a wider lens physically intercepts light rays coming from more extreme oblique angles.
Okay.
So the glass of a 150-degree lens is capturing photons that had to travel longer, more convoluted paths to reach the camera compared to a narrow 45-degree lens.
So in instantaneous math, you just draw a straight line from the object to the observer and call it a day.
Right, but in the blender simulation, the physical hardware of the camera eye dictates which delayed photons are captured.
The local image that the camera renders is fundamentally distorted by the physical journey of those specific light rays.
The visual data depends entirely on the physical properties of the observer.
Wow. Okay, let's take this concept out of the rendering software and put it in a gritty, high-stakes physical scenario, because the author moves from Blender to a World War II tank battle.
Yeah, to expose a massive blind spot in standard theoretical physics.
When you open a textbook to learn about relativity, you inevitably encounter the thought experiment of a moving train, right?
Always a moving train.
The train moves left to right along the x-axis, and maybe a light beam bounces up and down on the z-axis.
But the analysis is almost exclusively two-dimensional.
They completely ignore the axis, they ignore depth, they ignore the literal space sitting directly between the object and the observer.
And the author sets the stage precisely to isolate this y-axis depth. Imagine you are sitting in the driver's seat of a red tank. Your position on the axis is -100.
Okay.
Directly in front of you, 200 units away at +100, sits a blue enemy tank.
So if I look through my tank's reticle and spot the blue enemy tank at exactly time 0, I am not seeing the tank as it exists in that precise microsecond.
No, you're looking at 200-second-old light that finally finished its journey across the battlefield to hit your retina.
The optical illusion of the universe begins right there.
Because light has a strict speed limit, every observation across depth is an observation of the past.
But the ultimate conclusion of the author's theory really hinges on what happens when your red tank starts moving.
This is where it gets crazy. If your red tank drives forward through the electromagnetic field toward the blue tank, you are no longer passively waiting for the light to cross the 200 units of depth.
You're actively driving into the light.
Yes.
We are creating a headwind.
A headwind of light. The global absolute speed of light traveling through the electromagnetic field Romer's coordinate system remains completely constant.
Right.
But your local visual measurement of that light fundamentally shifts. If you're parked, a photon from the enemy tank takes a set amount of time to cross a specific unit of distance.
But if you're rushing forward to meet the photon, you're closing that physical gap. That light hits your camera eye faster than it normally would.
The apparent speed of the light changes relative to your local moving coordinate system.
And because my eye is intercepting that visual information faster than it should, the image of the blue tank I see through my reticle becomes compressed.
The horizontal field of view distorts.
I am literally driving into a delayed stream of photons, warping the visual data.
And this specific mechanism, this optical distortion caused by the headwind of light, brings us to Hendrik Lorentz.
Lorentz, the physicist who created the Lorentz transformations.
Yes.
These are the foundational mathematical equations that Einstein utilized to prove that space contracts and time dilates when an object moves at high velocities.
And the author makes a staggering claim about these equations. Lorentz's math meticulously describes how an object appears to shrink length contraction and how time appears to slow down time dilation.
Right.
But the author argues these equations are not describing a mystical, literal bending of the fabric of space-time. Instead, they're functioning purely as a mathematical patch.
A patch. Like a bug fix in a video game.
Exactly that. Because theoretical physicists were working in God mode, completely ignoring the physical delay of light traveling across the depth of the axis, their mathematical models didn't match the strange, distorted reality of high-speed observations.
Ah, so when things moved incredibly fast, the local visual data skewed due to the optical headwind effect.
Yes. And according to the author, Lorentz's equations simply act as a mathematical formula to squish the object on paper, correcting those distorted local visual measurements so they align with the global physical reality.
That is a phenomenal shift in perspective. It's like looking through a funhouse mirror that squishes your reflection. And instead of realizing the physical glass of the mirror is curved, you write a brilliant Nobel Prize-winning mathematical proof declaring that the actual physical universe is wavy.
You've taken an optical illusion caused by the mechanics of light and declared it to be the fundamental law of reality. It is the ultimate consequence of mistaking the map for the territory.
The author's thesis is that relativity essentially took a mathematical correction for an optical delay and enshrined it as physical law.
By ignoring the physical camera eye, physics lost its grip on the mechanics of the actual world.
So, bringing this profound, century-spanning physics argument back down to you, listening right now, why does the delay of light in a World War II tank battle matter for your life?
It's a fair question.
The ultimate takeaway here is the danger of relying purely on abstract models without interrogating the mechanism of how you gather your information.
Whether you're prepping for a crucial boardroom meeting or analyzing real-time financial data.
Or trying to predict user behavior from a dashboard. If you rely purely on your sandbox spreadsheets without accounting for the physical, messy, delayed reality of how that data traveled to get to you, you will draw distorted conclusions.
You cannot manage your life in God mode.
You have to account for the camera eye. You have to account for the delay.
Which leaves us with a rather provocative concept to examine in our own lives. The author meticulously demonstrated that ignoring the physical travel time of light across the axis, ignoring the depth, distorted our foundational theories of the physical universe for over 100 years.
The greatest minds in science assumed things were happening instantaneously when physically they were not.
They trusted the instantaneous map over the delayed territory. So consider our modern digital worldview.
We live our lives mediated through screens.
We do, implicitly assuming the information we receive, the breaking news, the stock market fluctuations, the social media feeds, is instantaneous and perfectly representative of global reality.
But what if it isn't?
Exactly. If the world's most brilliant physicists could have their entire understanding of physical reality skewed simply by ignoring the physical delay of information reaching their eyes. Wait, let me rephrase that. If they could get it wrong just by ignoring that physical delay.
How much of our own immediate, real-time digital worldview is actually built on a delayed, distorted headwind of information?
Are we reacting to the world as it currently is? Or are we making decisions based on distorted ghosts of data that have already passed us by?
Are you seeing reality or just an optical illusion in the reticle of your tank? You can't stay in God mode forever. Eventually you have to look through the camera.